This is my first time that my talk is being recorded, so I'm a little bit pressured. I cannot make a mistake. I mean, I'm not allowed to lie, even unintentionally, right? Okay, so today, I'm studying matroid theory and hyperplane arrangements, and so also I'm interested in moduli theory. And today I'm going to talk about the matroid-based polytopes associated to hyperplane arrangements. So let me begin with the definition of convex polytope. Convex polytope is a convex hull of finitely many vertices, points. So convex polytope Q is defined as convex hull of finite points in Rn for some n. Okay, so for finite sets. And we can describe this another way, in another way, like this. Intersection of half spaces, which is bounded, that is bounded, should be bounded, where Hj is a half spaces. So the inner product of X and Uj for some J is bigger than or equal to 0 for some non-zero vector. So let me introduce a notation first. For a vector in Rn, square bracket n denotes a set n through 1, 2 up to n. And for some subset of bracket n, Vi denotes the sum of ith entry contained in I. So, okay, then an indicator vector of B, a subset of B, denoted by 1B, is defined like this. 1B I is 1 if I is contained in B, otherwise 0. Okay. All right, and then so the Q, the convex hull of indicator vectors of B such that the script B satisfies the followings. So all elements has cardinality K, non-zero cardinality K, and then any edge of Q has length 1. Yeah. So this kind of Q, so Q is called a matroid polytope. Called a matroid polytope. Okay, easy definition. So example. So this line segment with length 1. This is matroid polytope. Is that true?
So for that one there, what's K, what's?
Yes, yeah. N is 2, so I label it 1 and 2. The vertices, I label it 1 and 2.
Okay, so
and the length is 1.
So this goes from the point 0, 1 to 1, 0?
Yeah, okay. So.
Right, the first indicator vector is 0, 1, the second one.
This K is in this case 1. Uh-huh. Yeah, so
in R2 that has length square root of 2.
okay, so then 1, what's that? 1 is 1 and 0. Okay, so 1 and 2 is 0 and 1. And it doesn't have edge, non-zero length edge, because this is one-dimensional thing. Well, this is a little bit exceptional case because it doesn't have length. The edge doesn't have length. So another one is this one. So 3 vertices. And regular triangle, and then so I label it 1, 2, 1, 3, 2, 3. In this case, n is 3 and k is 2. So 1, 2 means set 1 and 2. And this is 1 and 3, and this is 2 and 3. The three-dimensional thing is maybe this one, octahedron. So label it 1, 2, 1, 3, 1, 4, and this one is 2, 4, 2, 3, 3, 4. Okay, octahedron. So upper half is also what's that? The matroid polytope by definition, because all the edges has length 1, have length 1, and that satisfies that conditions. So even like upper one, upper half. This is also matroid polytope, and the middle pane also lower half is matroid polytopes. Okay. Yeah. And then now, what is matroid? Matroid is a combinatorial notion of a spanning set of a vector space. So let me define it formally. So matroid is a pair of finite set and a subset and a certain subset of the power set of n. So bracket n. So matroid, a matroid is a pair, so bracket n and some script b, such that B is a sub-collection of the power set n, such that every element in it has cardinality k, And then second, for two members of script B, for any x contained in B1 but not in B2, there exists a member of B2 not in B1, such that B1 union minus X, and the union Y is a member of B. Okay, so this is called the matroid, and then the elements of script B are called bases of M. Okay? Bases of M. Matroid. Any question, Spencer? Okay. So, yeah, as you see here, this number 2 condition has something to do with this number 2 condition. But the relation is not obvious. We need some argument. Okay, and then any subset of any subset of any subset of a basis is called independent set. So for fix B of fix an element of script B, then every subset of B is called independent sets. Independent sets of M. Okay. Okay. Then so let script I be a collection of all such subsets I, B, such that B is a member of script B. So, and then, then it is known that if you are given a collection of base, then you can recover the script I, and also if you are given a script I, then you can recover script B. It's easy, right? Just if you are given a script I, then take all maximal elements, inclusionized maximal elements. Here I should say I satisfies the followings. First, it is not empty. Empty set is an independent set. And second, for if I is an independent set and then J is a subset of I, then J is contained in J is an independent set too. And if you have two different independent sets of different cardinalities with, for example, bigger like this, then there exists a member, an element of J not in I here, such that when you add J to I, it is an independent set. And here, this K, where is this K? This K. This K is called the rank of the matroid. So it's called rank of the matroid M, and denoted by Rm. Okay. Then, so now restriction of a matroid to M, U is defined like this. M of U, M restricted to U is a pair U and BU for some U, subset of U, and the script B restricted U is the basis contained in U. Okay. Then this is a matroid. Okay. Restriction is this is a matroid. Then now I define a rank function of a matroid. So fix a matroid. M is a matroid. Then define the rank function of M as follows. So R is R maps the subsets of N to a number R of M restricted to U. Okay. Okay. So this is called the rank function of M with subscript M. Then rank function satisfies the following. So R satisfies the following. First, R of U is bounded by the cardinality of U for all U. And second, if U is a subset of T, then R of U is less than or equal to R of T. And third one is RU union T plus RU intersection T is less than or equal to R of U plus R of T. And this property, this condition is called submodularity. I remember that the measure function satisfies this one, right? Upper measure in analysis. Anyway, okay, and then okay. So it is known that so you can describe matroid with a rank function or basis or independent set functions, but still they are all equivalent. So so I'm saying we can recover from another condition to another condition. Yeah, so equivalent. And R of okay, so B is contained in B, script B, if and only if R of B is cardinality of B, which is the rank of M. Okay? So then I is contained in script I, if and only if the rank of I is equal to the cardinality of I. 15 minutes. Okay. Yeah. So now let me introduce the dual matroid of a matroid. So dual matroid, for a dual matroid, M asterisk, okay, M star is a pair of a finite set and some collection of subsets of n such that independent set of M dual is defined as follows. Where is it? N bracket n subtract I is a spanning set. Spanning set of M. So what is spanning set? Spanning set J means R of J equals R of M. Okay, and then so base polytopes then here, so let 1 is 1 through 1, then we have the following property 1 minus did I define base polytope? Yes, I did, but okay, yeah. So okay, so move something up. Oh, yeah, here. So, okay. So I have to define a base polytope. Another polytope. Let me not call it base polytope yet. The BPM. So define BPM like this: X set of points of Rn such that ith entry is between 0 and 1, and sum of entries, whole entries, is the rank of M, and then X of U is less than or equal to R of U for all U. Okay, then there is theorem that this polytope, this convex polytope, is a base polytope. Okay? So now we have explicit description of a base polytope. So
is that related to how is that related to the polytope you started out with?
The one is like this.
You have this polytope Q.
Yeah. That's a good question. Theorem. So let me state this first. Theorem. So BPM is a base polytope. Such that what's that? The vertices. So and okay, base polytope. And if Q is a base polytope, then there exists a matroid such that the vertices 1B. So what's that? Then this pair B subset of N with 1B is a vertex of Q. This is a matroid. And BPM equals Q. Okay, this is theorem. So vertex corresponds to a base element of a matroid. Okay, now then Okay, base polytope has very nice property. Is let this what is that? This take one represent a vector 1 through 1, and then so the involution of a base polytope is a base polytope of a dual matroid. So this is really nice property. Okay, and where we can consider the independent set polytope as a convexor of independent sets, also spanning set polytope as a convexor of one J with J spanning set. But these two do not have this property. Okay, and also recovering the other two polytopes is much easier. Okay, so we pay attention to this kind of polytope, base polytope. Okay, now the representable matroid. Well, okay, representable matroid. With rank function R. If there exists a vector space V isomorphic to the k-dimensional vector space and a spanning set Fi spanning set of V such that the rank function coincides with dimension of span of Fi. Okay. So this is called representative matroid. So for example, in R2, this origin and this vector 1, V1, F1, F2. Okay, and R2, V is R2. Then F1 and F2 is a spanning set of V, and then also this condition is satisfied. So here 2 and the given rank function. This is representative matroid. Okay, so then why do I study matroid? Because hyperplane arrangement has a matroid structure. Hyperplane arrangement, to me, is a pair hyperplane arrangement is a pair of projective space of k minus one dimensional projective space with hyperplanes with no common intersection. So without any common intersection. So intersection of d I is empty. Okay. Here, let Fi be the homogeneous linear defining equation of di. Okay, then we see that what then this one, so N and R is a matroid, representative matroid actually. Representable matroid with the rank function R of U is the codimension. Okay, so PV, where V is k dimensional, then V star of spanned space by Fi, where I is contained in U. Then we can consider those hyperplane arrangements. So like this. So P1 and 3 points. Okay. And then, okay, and 4 points. Like this. But actually, I'm considering the equivalence classes, isomorphism classes of hyperplane arrangements. So in this case, the dimension of those spaces is 0 because there are only 3 points. And in this case, the dimension of the hyperplane arrangements is 4 minus 3 is 1. So on P2 with 4 lines, so dimension of the hyperplane arrangement is what? So there's no freedom for these lines, so this dimension is 0. And if I have one more line, the hyperplane arrangement, the space of generic hyperplane arrangements. So in this case, then here, so 1, 2, 3, 4, 5. Then in this case, the dimension should be 5 minus 4 times. So this one has 2. So 2 freedom 2, so it's like k minus 2, so 2. So the dimension is 2. Maybe I better describe hyperplane arrangements in terms of matrices. So you can consider the matrices. This with column vector F1, F2, Fn, and then you and we projectivize it. Okay, and then modify the torus. Here, torus is multiplicative group of F given field modify, the diagonal action of GM, and then also the symmetry. So P, G, L, K. So we're considering the isomorphism classes. So we say this is the space of generic hyperplane arrangements in this case. Okay, 4, 3, 4. Oh, so is that 3:15? Oh, okay, all right. And then so okay then. So hacking, kill, develop, compactified. This space H hyperplane arrangements with Kn, and we call it M bar Kn, and they show that a special fiber this X lambda is reducible components of X. Reducible components. So for a special fiber, so there exists an one-to-one correspondence between the strata of X and the strata of tiling of delta. That is not contained in the hyperplane, coordinate hyperplanes. Here, this means the union of coordinate hyperplanes. Okay, so the strata of X and the strata of this. Your tiling means tiling of delta Kn. Your delta Kn is hypersimplex. Define like this. Actually, this is the base polytope of uniform matroid Kn. Anyway, So tiling is a face-fitting collection of base polytopes. Face-fitting collection. Of base polytopes. Okay. Which is decomposition of delta. And then how do I?
Application is coming from Jaeho.
Yes, Alexev. So yeah, so this guy hacking killed Tevelev did not use GIT construction of this. They said they use some more elementary way, but Alexev constructed this with weight. So weight means weight vector, so weights to hyperplanes.
So maybe I can make a remark. So this is the same as the compactification coming from the topical Rosman.
For the hacking killed Tevelev. Okay. So
And the other one, the wave one, that's the Hasid compactification?
that is, yeah, M2, this one. Well, I don't know, the notation will be maybe M0 beta bar, I think. But this is general notation due to Alexeyev. So these two means 2 minus 1 is one dimension. So curve. Okay. The rank K, 2 minus 1. So N marked points with weights. So yeah, so then, so yeah, as K, so maybe M2 4 bar. Then the element of this, general element looks like, generic element looks like this. P1, 1, 2, 3, 4, right? And then now consider this situation. 3 and 4 collide each other, getting close, and then at last they coincide. Then what happens? Then in this complex equation, the geometrical interpretation is this one. A new branch pops up, and 3 and 4 move to another branch. So this node. So this. Yeah. So then this is contained in 2, 4 bar. And as this theorem, what that theorem says is this. So this is a one reducible component of x1, like x2. Okay. Then so 1, 2. So that corresponds to upper half of octahedron here. 1, 2 is the base of this one. So these correspond to 1, 2, 3, 4. This hyperplane arrangement, and the base is 1 and 2 in this case. So 1, 2, and then the x2 correspond to this bottom one, bottom half, 3, 4, and then this node correspond to x1, x2, and this node correspond to this one. Okay. 1, 2, 2. Am I? 1, 2, 1, 1. So 1, 3, 1, 4, 2, 4. Okay, so All right, and then so I'd like to say this one. All right, well, this is my viewpoint. Matroid is actually equals hyperplane arrangement. Equals hyperplane. Why is that? Because I have to say here, matroidal hyperplane arrangement. Matroidal hyperplane arrangement. That's because if you give me a matroid M, then I consider this pair M and M here on matroid M, loopless matroid. Sorry, loopless. Loopless matroid is loop. Loop means I use a loop if rank of I is 0. Okay, but if the matroid comes from hyperplane arrangement, then any singleton cannot have rank 0, right? So loopless. If you give me a loopless matroid, then I consider this pair. Okay. Then this pair records all the combinatorial information of the hyperplane arrangements. So for example, so in this case, 1, 2, 3. If this is the hyperplane arrangement, then M is what? What is the base? The base of M should be 1, right? And 2, 1 and 2, because it is 2 minus 1. Okay, so rank is 1 and 2. And 1 and 3, and 2 and 3. Okay. Actually, looking at flats is much easier than looking at bases. A flat means here flat F. So I have to say the closure operator first. Then closure operator is for a subset of n, the closure of A is this one. Such that, so if it doesn't increase the rank of A, then you add it to A. So rank of A union X is R of A. Then the flat means F is a flat if its closure is equal to itself. F bar is F. Okay. Then, okay, so in this time I give another example. So 1, 2, 3, 4, 5. Okay, then I can read off the flats immediately here. So where is 1 is flat, 1 rank. So here rank 0, 1, 2, 3. Then these flats, then rank 0 is empty set flat here, and the rank 1 is flat. Rank 1 flat is 1, 2, 3, 4, 5. Rank 2 flats are, you see, so 1, 2 is not a flat, but 1, 2, 3 is a flat, right? So 1, 2, 3. So so each vertex, the intersection point correspond shows the flat. So for this case 1 to 3, in this case 3, 4, 5. In this case was 1, 1, 5. And the whole thing is what? N. 5 like this. Okay. So also I want to say the notion, I want to tell you the notion of separability, separators like that. The separator is defined like this. Separator. T is called the separator of M if it separates the rank function, then it is called the separator. Then empty set and the whole set is always separators, so we call it improper separators. Improper separators. So M is called separable if it has if M has separators. Proper separators. So okay. So I told you that the matroid is the same thing with the hyperplane arrangement. Matroid hyperplane. In this case, is a matroid separable? It's not, because you cannot separate it to like rank of this matroid is 2, right? Then should be, because it doesn't have any loop there, because this is loopless matroid. So to separate 2, this is the only way to separate the 2. But here, see, the rank, it has a rank 1, and rank 2, right? So each one has rank 1. So how to separate it? So this is not separable matroid, but this one, like 1, 2, 3, 4, T1, this is separable matroid. Now 1, 2 has rank 1, 3, 4 has rank 1. So whole rank is 2, so it's separable matroid. Okay, so yep. So let me tell you then one very interesting algebraic geometry fact. So yeah.
Before you go further, I still don't understand the statement matroid equals matroidal hyperplane.
Okay, cool.
So if you take a non-representative vector, what is on the right hand side?
That's this one. The pair. This is pair. Then the geometric lattice, the collection of flats describe the intersection information of hyperplane. So I call it matroid hyperplanes. So I call this one this call it abstract or matroidal hyperplane. Okay, but if it is not, even if it is not representable, so I call it matroid hyperplane. And then so here, let F be a flat, and then okay. So these intersect. So let's consider this one. Okay. J. This defined as M. Did I define contraction? No, right? Contraction is like here. So contraction M, contraction T is defined by a rank function R M T such that so 2 n minus t to here such that here U is mapped to R of U union T minus R of T. Formally looks like this, and in graph theory it means, in graph theory, graphing matroid means what? The labels of edges, and then some set of cycles. So if 1, 2, 3, 4, if you contract 1, that means you contract. Okay? So they correspond to this. So in this case, this will be INJ bar, flat. So the F, this is the geometric lattice, I mean a set of flats of matroid. Then this describes the intersection information of hyperplanes. Okay? So this makes sense. So if a matroid is representable, then this matroid hyperplane arrangement is also representable, and vice versa. The same thing. Okay, so why matroid theory is interesting is that like this. Okay, so let's consider here K equals 3. I mean two-dimensional line arrangements, and okay, so K3, fix K3. Okay. Then there's theorem that fix K3. Then there exists at most one degenerate flat, rank 1 flat, degenerate rank 1 flat of M. So degenerate means, so definition, so F is non-degenerate flat, non-degenerate flat or flaccid. I think this flaccid, Dr. Stamfels called this kind of object flaccid, and this non-degenerate flat comes from the paper of Gelfand Serganova paper. If M restricted on F and M contraction over F both are inseparable. Okay, inseparable. So degenerate means one of these is separable. So this theorem is by simple computation. Then by this one. Well, so suppose that then there exists a degenerate flat. Then rank 1 flat is always inseparable. You cannot separate one properly. So this is rank 1 flat. So suppose that this is the this rank 1 degenerate flat. Then the hyperplane arrangement looks like this. No other choice. Maybe like this. Whatever. 1, 2, 3, 4, 5, 6. Then there is a theorem that the flaccid of a loopless matroid are in one-to-one correspondence with the strata of the hyperplane arrangements. Well, no, not like this. I mean, flaccid of the loopless matroid M are in bijection with facets of base polytope of M not contained in the zero boundary. This is the theorem of Gelfand-Serganova. Now with this here now, so then you see this one. What is this? Maybe 1, 2, 3, 4, 5, 6, 7. Then 1, 2. So this point is what? This point corresponds to an inseparable flat, actually non-degenerate flat, flaccid. So you can consider like this. So well, but this one is degenerate. But all the other flats are what? Flaccid, non-degenerate. Then you can consider like this: blow up at this point, blow up this point. Okay, and then now every except this one, every divisor is what? What is it, like flaccid, corresponds to flaccid, and then actually this is what? -1 curve, and then you so well, I can consider like what? Blow down this one, contract it, then you get this kind of thing. And this is P1 cross P1. And what I want to say is that matroid theory connects, it just captures combinatorial information of hyperplane arrangement, and it helps our understanding of hyperplane arrangements. So, and moreover, so very recently, Alexev proved that the log canonical models of the hyperplane arrangements. So P2 BI, in this case divisor, so I write down like this. Or B is either P1 cross P1 like this, or blow up of P2 at the points. These kind of points. This is not LC point. So yeah, isn't this very interesting? So okay, so how much time do I have? Minus. Yeah, so I think I was too nervous. Final statement is that so it's like this. So let me make a final statement. Okay, so final statement is that very interesting. Is that let BPMI be a collection, phase-fitting collection of base polytopes with common intersection this is a codimension 2 face, common face, codimension 2 common face. Okay. Then now that we consider normal slices, consider the normal slice to Q, then it looks like this. 5 pictures. So this that correspond to represent Q. Then like this. One, two, yeah. 3, 4, 5. Only 5 cases. So convex polytopes. This is not the case for the general convex polytopes. But base polytopes are special kind of very special convex polytopes, and they have this kind of gluing property. And for k equals 3 case, if k equals 3, then this picture also represents the picture of variety. So what? So we can classify the M36 bar combinatorial types of M, the elements of this, but actually that is exactly the classification of this one, because and it looks like this. Yellow one. And then this, and so on, like this. And then dual graph of this, dual graph means, vertex for each, two-dimensional indexable component. Those
Ribbon graph? Or, so ribbon graph is the
dual graph.
No, he's
I haven't.
a ratio of lines. Pseudo lines.
Yeah. Okay. And the dual graph of the one more. Is the dual graphs coincide with the generic tropical generic lines in TP5. I mean, I don't see exactly how they coincide, but they coincide.
Is complete?
Yes.
Done?
Yes. I think I'm done. Thank you for your attending.